Welcome back. Today, we're really going to level up our understanding of double integration, taking it way beyond the basics.
So, last time, we got the fundamentals down, right? We figured out how to calculate the volume under a surface as long as the base was a nice, simple rectangle with straight sides.
But let's be real, the world isn't built out of perfect boxes. So what happens when your area is defined by curves? Like, say, the little sliver of space trapped between a parabola and a line. How in the world do you handle that?
Okay, here's how we're going to tackle this. First, we'll break out of the rectangle. Then I'll show you a super clever trick for when an integral looks impossible. After that, we'll unlock a kind of superpower using a polar perspective. We'll see it all work in a real example, and then we'll talk about why this stuff actually matters so much.
All right, first things first. We've got to develop a tool that can handle these more complex, general regions, not just simple squares.
So the big idea here is something called variable limits. Just picture this. As you scan across a shape along one axis, let's say the x-axis, the top and bottom boundaries aren't just flat lines anymore. They're changing. They're defined by curves or functions. And you know there's a super reliable 4-step process to nail this every time. Step 1, and I mean this is the most important, you've got to sketch the region. After that, you just decide if you're slicing it vertically or horizontally. Your inner limits will be the two curves that your slice is stuck between, and your outer limits are just the absolute start and end points of the whole shape. So let's take our example. For every single x value between 0 and 1, that little vertical slice we're imagining, it always starts on the bottom curve, the parabola, and stretches up until it hits the top curve, the line. So those two functions literally become our new limits of integration.
Okay, now that we've got that down, let's add a seriously powerful new tool to our belt: changing the order of integration.
So picture this. You set up your integral perfectly, you follow all the rules, and then you look at it and just go, uh-oh, the function you're supposed to integrate is an absolute monster. Maybe it's even impossible. Are you just stuck? Nope, not even close. This is where you can literally flip the script. It's kind of like slicing a loaf of bread, right? If cutting it vertically is making a huge mess, why not just turn it and slice it horizontally? You're not changing the loaf, you're just changing your approach. By switching our perspective from vertical slices to horizontal ones, we have to rethink our limits, but very often, the problem becomes way, way easier. And man, does this show you just how powerful a change in perspective can be. That integral on the left? Total headache. But just by rethinking how we slice it, we get the one on the right, which you can probably solve in just a minute or two. It's the same answer, just a much, much easier path to get there. Okay, but here's a quick heads up. Sometimes when you flip your view, what was one simple region now looks like it's in two separate pieces. A horizontal slice might run into different boundary curves depending on how high up you are. No big deal though. You just set up two separate integrals and add them up at the end. Okay, so we're good with general curvy shapes. But what about the really round stuff, like circles? For that, we're going to need a bit of a superpower. You know, if you try to describe a circle using our good old up and down, left and right, x and y coordinates, it gets ugly fast. You get these nasty square roots. It just feels wrong because it is wrong. It's the definition of trying to jam a round peg into a square hole. And this really gets at a core idea in all of science, right? Don't force a tool that's not working. Find the right one for the job. And that's where polar coordinates come in to save the day. Instead of x and y, we think in terms of a radius, r, and an angle, theta. It's the natural language of anything circular. But here is the most important part, the one thing you absolutely cannot forget. That little piece of area, dx dy, becomes r dr d theta. That extra r, that little guy, is the secret sauce, the magic ingredient that makes this all work. And just look at what happens. A shape like a cardioid, which is a total nightmare in x and y, suddenly has this simple, almost beautiful equation in polar coordinates. The integral to find its area goes from being a monster problem to something, well, pretty straightforward. All right, enough theory. Let's get our hands dirty and see this in action. We're going to tackle a classic problem, finding the area where two circles overlap. So here's our game plan, and it uses everything we've talked about. We sketch it out. Always, always step 1. we immediately notice it's symmetrical, which is a huge hint we can do half the work and just double our answer. But look closely. The boundary of that shared area is made up of two different circles. That tells us we're going to need two separate polar integrals, one for each piece. Then we just add them up. Boom, done. Okay, so we've just gone through some pretty heavy-duty math. You might be wondering, is this just some abstract puzzle? And the answer is a huge no. This stuff is at the heart of so much of modern science and engineering. I mean, just to give you an idea, a typical engineering student spends about 9 entire lectures just on this topic. It's not a side note, it's a foundational pillar. And why? Because you see it everywhere. You need to calculate the balancing point, the center of mass of some weirdly shaped airplane wing. That's a double integral. You're trying to figure out probabilities in a complex system. Double integral. Fluid dynamics, electromagnetism, physics. Yep, you got it. These tools solve real, tangible problems. So let's just take a step back and look at what we did. We have seriously leveled up. We went from being stuck with simple rectangles to being able to handle all kinds of complex, curvy shapes. And we learned that the key is often just changing how we look at the problem, whether it's flipping our order of integration or switching to a whole new coordinate system. So we've pretty much mastered the 2D world. But that leads to the next obvious question, right? What happens when you're not dealing with a flat area, but a full, complex, three-dimensional object? What then? Well, my friends, that question is our ticket to the next level, the awesome world of triple integrals.